Hello, today I'm going to work through a set of questions that you might typically get in an AS level physics exam on quantum phenomena. Question 1. We are told that there's a light emitting diode whose threshold voltage is 1.7 volts. That means you need to put 1.7 volts across it before it will light up. We're told that the light has a wavelength of 7 times 10 to the minus 7 meters. We know that the speed of light is 3 times 10 to the 8 meters per second, and we are asked to find the energy of the photons that are emitted, and we need to calculate Planck's constant h. Now, we don't need to go into the detail here, but we know that when you get light, or rather photon propagation at atomic level, the reason is that you will have had an electron that will have been given energy to promote it to a higher level, a higher energy level. And then when it gets to a higher energy level, it will always want to fall back to its ground state. And when it does so, it gives off that energy, and it gives off that energy in the form of a photon. So the idea is that by putting 1.7 volts across the light emitting diode, we are giving it, the electron, enough energy to jump up to the next energy level, from which it then falls, and it gives off that energy as a photon. So it must be giving off 1.7 volts, but volts is not a measure of energy. The energy term that we use is an electron volt. And an electron volt is a measure of energy. It represents one electron being accelerated through 1 volt. So the energy of this electron, or the energy that this electron absorbs in order to be promoted, is actually 1.7 electron volts, and when it falls down again, it gives off an energy of 1.7 electron volts. Now, the electron volt is not an SI unit, so we must get it in the right unit of energy, which of course is joules. So to convert electron volts into joules, you multiply by the charge on the electron, which is 1.6 times 10 to the minus 19 coulombs. So effectively you take the 1.7 electron volts and multiply that by 1.6 times 10 to the minus 19, and that gives you the energy in joules, which is 2.72 times 10 to the minus 19 joules. So now we've got the energy in the correct unit. Now we're going to use the tried and tested formula that E equals hf. The energy of the electron is Planck's constant times the frequency. Well, frequency is just speed divided by wavelength, so now we can say that energy is hc over lambda, and that means that we can write that Planck's constant is equal to E lambda over c. Just rearranging this formula here. Well, we know that means that Planck's constant is equal to E. E we've just calculated, 2.72 times 10 to the minus 19. Lambda we were given, it was 7 times 10 to the minus 7 meters. And of course the speed of light we were given, 3 times 10 to the 8. And if you calculate all of that, you should get 6.3 times 10 to the minus 34 joule seconds. So we've done the calculation for both. We've calculated the energy of the photon, that's what we were required to identify, and we've calculated Planck's constant, which we were also required to identify. Question 2. We are told that the work function for aluminium is 4.06 electron volts. We're asked to find the threshold frequency for the photoelectric effect. And we recall that the photoelectric effect, in this case, you've got aluminium, you've got light shining down on the aluminium, and if the light is of sufficient frequency, you'll get electrons emerging. But those electrons will only emerge if there is enough energy in the photons of the light to completely kick the electrons out of the atom. And we've been told that the binding energy, or the work function, or the energy you need to kick an electron out of an aluminium atom is 4.06 electron volts. So essentially, if you draw the binding energy diagram, what you've effectively got, if this is E equals 0, then the binding energy, or work function phi, is minus 4.06. In other words, it's a minus term because it's actually held within the atom. You have to give an electron sitting in this position 4.06 electron volts of energy to get it out of the atom. And we know that E equals HF, where F is the frequency. So the question is, what frequency do you need, since H is a constant, what frequency do you need to get sufficient energy to kick the electron out? In other words, to give it 4.06 electron volts. Well, now it's just mathematics. So we've got E equals 4.06. Now remember, that's electron volts. We need it in joules for SI units, so we have to multiply by 1.6 times 10 to the minus 19, and now we've got a value in joules. E is equal to HF, so consequently F is equal to E divided by H, and that means frequency is 4.06 times 1.6 times 10 to the minus 19 divided by Planck's constant, which we can take as 6.3 times 10 to the minus 34. And I think if you calculate that, you will get 10.3 times 10 to the 14 hertz. So that is the threshold frequency. That frequency will give an energy which will just get the electron out of the atom. It won't have any kinetic energy, so it won't go anywhere, but it will just sit outside the atom. If the frequency is greater than this, then you will actually give the electron enough energy not only to get out of the atom, but to have some residual kinetic energy as well. Question 3 relates to the photoelectric effect with copper. The work function, or binding energy, for copper is 4.7 electron volts. That's the energy you need to give to an electron to kick it out of the copper atom. And we're using light with frequency 2.2 times 10 to the 15 hertz. And we're asked to find the energy of the photon and the maximum energy, or the maximum kinetic energy, of the emitted electron. Well, to find the energy of the photon, we're just going to use the standard E equals HF. And that's going to be, H is 6.3 times 10 to the minus 34. And the frequency we were given was 2.2 times 10 to the 15 hertz. And that is going to be measured in joules. If you want it in electron volts, which we will for these purposes, it's going to be the amount in joules divided by 1.6 times 10 to the minus 19. So to convert from electron volts to joules, you multiply by 1.6 times 10 to the minus 19. To convert from joules to electron volts, you divide by 1.6 times 10 to the minus 19. And that, if you do it, I think comes to 8.66 electron volts. But phi, we've been told, the work function, the binding energy, is 4.7 electron volts. So consequently, you only need 4.7 electron volts to get the electron out of the atom. The remaining energy will go into kinetic energy. So the kinetic energy of the electron is simply going to be the difference between 8.66 and 4.7, which I think is 3.96 electron volts. So the kinetic energy of the electron is 3.96 electron volts, and the energy of the photon is either that in joules, if you want it in joules, or 8.66 electron volts. Question 4. We're given this energy level diagram, obviously not to scale, for an atom, and we're told that an electron is accelerated through 12.1 volts. We're asked to find the kinetic energy of the electron both in eV and in joules. We're asked to find what level the electron would be excited to if it were originally in the ground state. And then thirdly, we're asked to identify the three energies of resulting photons that might arise as a result of that excitation. Well, we know that the electron is accelerated through 12.1 volts. And the definition of an electron volt is one electron accelerated through 1 volt. So if you accelerate one electron through 12.1 volts, then the energy of that electron will be 12.1 electron volts by definition. We also need to specify that in terms of joules, and I've already told you that to specify in joules, you can convert from electron volts to joules by multiplying by 1.6 times 10 to the minus 19, and that is going to come to 1.9 times 10 to the minus 18 joules. The next question is, to what level will the electron, which is initially in the ground state, be promoted if it is given 12.1 electron volts of energy? So it's given plus 12.1 electron volts, and it is at a minus 13.6 electron volts state. So plus 12.1 minus 13.6 is equal to minus 1.5. Consequently, the electron will be promoted to the n equals 3 state. Now we're asked to find the energies of the three photons that might materialize as a result of that excitation. Well, the point is that having been excited to a higher level, the electron will want to return to a lower level, and it can do that either by dropping straight back down to the ground level, in which case it will emit energy between the two, or it can fall initially to the n equals 2 level and subsequently to the n equals 1 level. And you will get photons from each of these transitions. So it's just a case of subtracting the energy levels. In this case, it's exactly the reverse of going up. So it's 13.6 minus 1.2. The energy of the photon would be, if it's going from 3 to 1, would be 12.1 electron volts. On the other hand, if the electron is going from 3 to 2, then the difference here is 1.9 electron volts. So energy of the photon going from 3, which results from the electron falling from 3 to 2, is going to be 1.9 electron volts. And finally, the electron falls from 2 to 1. That means it gives up 10.2 electron volts of energy, and so the photon, the emerging photon, which emerges from the 2 to 1 transition, will be 10.2 electron volts. Question 5. Calculate the energy in joules and electron volts of a photon of wavelength 6 times 10 to the minus 7 meters. Well, here we're going to use the classic formula E equals HF, which of course is E equals hc over lambda, since the frequency is the speed divided by the wavelength. Planck's constant h is 6.63 times 10 to the minus 34 times the speed of light, which is 3 times 10 to the 8th, divided by the wavelength of the light which we were given, that was 6 times 10 to the minus 7. And that of course is going to be in SI units, so that's going to be in joules, and that comes out to be an energy of 3.32 times 10 to the minus 19 joules. To convert that to electron volts, I said if you convert from joules to electron volts, you divide by 1.6 times 10 to the minus 19, which is the charge on the electron, and so you get in electron volts, it will be 3.32 times 10 to the minus 19 divided by 1.6 times 10 to the minus 19, and that is going to come out at 2.08 electron volts. Question 6. What is the velocity of an electron whose wavelength is 6 times 10 to the minus 7 meters? Well, now we need the de Broglie equation, which you may remember is P equals h over lambda, that's the momentum, is equal to Planck's constant divided by wavelength, which means we can rearrange that to say that lambda, the wavelength, is h over p. And since for an electron, momentum is mass times velocity, that equals h over mv. Now we can rearrange this formula for velocity, which is what we want. The velocity is going to be h divided by m lambda. And now it's just a case of substituting the values. Planck's constant is 6.63 times 10 to the minus 34. The mass of an electron will be given to you, 9.11 times 10 to the minus 31 kilograms. And the wavelength you were given as 6 times 10 to the minus 7 meters. And that is therefore going to give you a velocity which turns out to be 1213 meters per second. So 1213 meters per second. Question 7. We are told that an electron has a velocity of 3.5 times 10 to the 6 meters per second, and we are asked to find its wavelength. So once again we can take the de Broglie formula, that P equals h over lambda. The momentum is Planck's constant divided by wavelength. We can rearrange that to say that lambda equals h over p. Sorry, that means lambda is h over p. And since for an electron momentum is mass times velocity, that's h over mv. So now we've got that lambda, the wavelength, which is what we're trying to find, is h over mv. Once again, it's just a case of substituting. H is 6.63 times 10 to the minus 34. The mass of the electron, once again, is 9.11 times 10 to the minus 31 kilograms. And we were told that the velocity was 3.5 times 10 to the 6 meters per second. And again, the calculator will give you that the wavelength of the electron, 2.08 times 10 to the minus 10 meters. Part 2 of this question asks us to find the velocity of a proton which has the same wavelength as the electron we just identified, 2.08 times 10 to the minus 10 meters. Well, we're going to use the formula that the wavelength is equal to Planck's constant divided by mv. We've already derived that here. Wavelength is equal to Planck's constant divided by mv. And consequently, that means that the velocity is equal to Planck's constant divided by m times lambda. And now it's just a case of substituting for a proton this time. So v is equal to h. Well, Planck's constant doesn't change. That's 6.63 times 10 to the minus 34. Divided now by the mass of a proton. That will usually be given you. That will be 1840 times the mass of an electron. So it's going to be 1840 times the mass of an electron, 9.11 times 10 to the minus 31 kilograms, times the wavelength which we calculated, 2.08 times 10 to the minus 10 meters. And again, if you put that through the calculator, you will find that that is of the order of 1900 meters per second. Question 8. An electron is accelerated through 5 kilovolts. We need to find 3 things. Firstly, the kinetic energy in electron volts and joules. Secondly, its velocity. And thirdly, its wavelength. Well, the first question is fairly easy. If one electron is accelerated through 5 kilovolts, then the energy that it will gain by definition is 5 keV, 5 kilo electron volts. If you want to convert that into joules, then you have to multiply by 1.6 times 10 to the 10 to the minus 19. So the energy in joules will be 5 keV. Well, you have to express that in EV, because to convert from EV to joules, you multiply by 1.6 times 10 to the minus 19 times 1.6 times 10 to the minus 19, and that gives you the energy in joules. And if you work that out, you should find that comes to 8 times 10 to the minus 16 joules. So that's part 1. Part 2, what is the velocity of that electron? Well, energy is kinetic energy, and that's going to be half mv squared. So consequently, v squared is equal to 2 times E divided by m, just by rearranging this formula here. And so once again, we can substitute. V squared is going to equal 2 times the energy, which of course we must express in joules. So that's times 8 times 10 to the minus 16, divided by the mass of an electron, 9.11 times 10 to the minus 31. And that gives you 17.6 times 10 to the 14. But of course that's V squared. So that means that V is equal to 4.2 approximately times 10 to the 7 meters per second. And the third part of the question was to find the wavelength, and here we're going to use the tried and tested that the wavelength is equal to h divided by mv, and that's going to be equal to 6.63 times 10 to the minus 34. That of course is Planck's constant, divided by the mass of the electron, which we know is 9.11 times 10 to the minus 31, times the velocity, which we just calculated, 4.2 times 10 to the 7. And if you work that out, I think you should find that that comes to a wavelength of 1.73 times 10 to the minus 11 meters. Question 9. We're given the energy levels of a hydrogen atom, and we're told that the spectrum for a hydrogen atom consists of 4 distinct lines: red, green, blue and violet. And we're told that the violet line represents the electron's transition from n to n equals 6 to n equals 2, and the photon that emerges is a violet line. The n equals 5 to n equals 2 transition gives a photon that is blue. The n equals 4 to n equals 2 transition gives a photon that is green, and the n equals 3 to n equals 2 transition gives a photon that is red. And the question we are asked is, why is there no visible photon for the transition 3 to 1? Well, we know that the formula that applies here is that the energy of the photon will be Planck's constant times the frequency of the photon. The energy is supplied by the jump from the different levels, and the frequency is calculated simply by taking that energy, and frequency times Planck's constant will equal that energy. So if you look at a violet line, that is coming from n equals 6 to n equals 2. Well, the n equals 6 we're not given, but it obviously is quite a small amount. So the violet transition is going to be of the order of 3.4 electron volts. N equals 6 will not be 0, but even if it were, then the energy difference between n equals 6 to n equals 2 would be 3.4 electron volts, and that would give you a violet line. Now, what is the energy transition between n equals 3 and n equals 1? Well, the energy from 3 to 1 is going to be the difference between 13.6 or minus 13.6 and minus 1.5. That is going to be 12.1 electron volts. Now, if 3.4 electron volts gives you a frequency which is in the violet region, what is an energy of nearly 4 times as much going to do to the frequency? Well, the frequency will be nearly 4 times higher. That means you're going up into the ultraviolet region, and you cannot see ultraviolet. So the visible spectrum for hydrogen consists of only those 4 lines. Any lines that fall down to n equals 1 will be in the ultraviolet region, and any lines that fall to the n equals 3 will be of a smaller energy than the red line, and that means they would go into the infrared, which again you cannot see with a visible camera. So as it happens, the only 4 transitions that result in visible light in the hydrogen spectrum are these 4. Everything else will either have a higher frequency because it's falling to the n=1 level, in which case it will be a ultraviolet, or if it falls to the n=3 or higher, it will have a very much smaller frequency than the red, which means it will be in the infrared. You multiply by the charge on the electron, which is 1.6 times 10 to the minus 19 coulombs. So effectively you take the 1.7 electron volts and multiply that by 1.6 times 10 to the minus 19, and that gives you the energy in joules, which is 2.72 times 10 to the minus 19 joules. So now we've got the energy in the correct unit. Now we're going to use the tried and tested formula that E=hf. The energy of the electron is Planck's constants that are emitted, and we need to calculate Planck's constant h. Now we don't need to go into the detail here, but we know that when you get light, or rather photon propagation at atomic level, the reason is that you will have had an electron that will have been given energy to promote it to a higher level, a higher energy level. And then when it gets to a higher energy level, it will always want to fall back to its ground state. And when it does so, it gives off that energy. Hello, today I'm going to work through a set of questions that you might typically get in an AS level physics exam on quantum phenomena. Question 1. We're told that there's a light emitting diode whose threshold voltage is 1.7 volts. That means you need to put 1.7 volts across it before it will light up. We're told that the light has a wavelength of 7 times 10 to the minus 7 meters. We know that the speed of light is 3 times 10 to the 8 meters per second. And we are asked to find the energy of the photon. Measure of energy, it represents 1 electron being accelerated through 1 volt. So the energy of this electron, or the energy that this electron absorbs in order to be promoted, is actually 1.7 electron volts, and when it falls down again it gives off an energy of 1.7 electron volts. Now the electron volt is not an SI unit, so we must get it in the right unit of energy, which of course is joules. So to convert electron volts into joules, and it gives off that energy in the form of a photon. So the idea is that by putting 1.7 volts across the light emitting diode, we are giving it, the electron, enough energy to jump up to the next energy level, from which it then falls, and it gives off that energy as a photon. So it must be giving off 1.7 volts, but volts is not a measure of energy. The energy term that we use is an electron volt. And an electron volt is a